Hey, good morning, everyone. Oh, wow, that's loud. I'm sorry, but maybe you guys can't hear me very well after last night anyway. Pretty fun show last night. Thanks, everyone, for coming out. Really great to see so many people up so early this morning. So our first talk of the day is Robert Seacord, who's talking about dangerous optimizations and the loss of causality.
Howdy. So I guess we're not recording this morning. The cameras seem to have disappeared. What's that? Yeah, I guess they were last seen with a couple of French-Canadian girls wandering down. Yeah. Okay. Okay, so the premise of my talk is that increasingly compiler writers are taking advantage of undefined behaviors in C and C++ languages to improve optimizations. So these optimizations can interfere with the ability of programmers to really understand the behavior of the code, and not only sort of human analysts, but also static analysis tools and so forth can also have trouble predicting the behaviors of different compiler implementations. So this sort of inability for programmers and tools to understand the behavior of the code can lead to increased software fault defects, and presumably some percentage of those are vulnerabilities. So this work originally was published as a vulnerability note some years back. This was actually in response to some Plan 9 developers at Bell Labs sort of discovered that their code that had been working had stopped working. And so we investigated and wound up publishing this vulnerability note. So I'm going to start by talking a bit about undefined behaviors. I guess a little bit about me is, I should have said this on the title slide. So I'm a principal security consultant at NCC Group. I've been participating on the C Standards Committee for a little over a decade now. So if you're wondering, who those idiots are that, define the C language and do all the stupid things. So, come tell me what you like least about the language. So one of the things I like least about the language is the definition of undefined behavior, because not that all these concepts aren't valid, but undefined behaviors was defined, I think, overly broadly in the standard. So it means one of three very different things. So first of all, it means that it gives license to compiler writers not to catch certain program errors that are difficult to diagnose. And so the C standard is written by C compiler writers for C compiler writers, and they're very friendly to each other. So they sort of pat each other on the back and say, if it's hard, you don't have to do it. And so that's how this comes about. The second is to avoid defining obscure corner cases which would favor one implementation strategy over another. And I have kind of a running example of this, but if you take int min remainder -1, mathematically that should give you a result of 0, but if you run that on an Intel processor, you'll get a fault. And so that's considered undefined behavior, so that implementations that compile for Intel platforms don't have to write a special case to check for that condition. But so that kind of gives you better performance, but it requires that the programmer is now responsible for guaranteeing that the code doesn't generate a fault. And the third case is identify areas of possible language conforming extension. So these are just places where the C standard doesn't specify some behavior, so an implementation can provide some implementation specific behavior. And a good example of this is fopen. There's a few mode strings, character modes defined, and any other character beside the ones listed are undefined behavior. And if you provide another character, you're unlikely to experience a crash of any kind. But that's really so that different implementations can add different modes that can be used to open a file. So regardless of why behaviors classified as undefined, An implementation can completely ignore that undefined behavior with unpredictable results. The thing we say most often in the C Standards Committee is the compiler could go off and play the game of life at that point in time, and that's perfectly within the bounds of the standard. It can behave in a documented manner characteristic of the environment. So for example, if you do int min remainder -1 on an Intel chip, characteristically that environment results in a fault. Or it can terminate a translation or execution with a diagnostic. So the basic design of an optimizer for C compiler is the same as for any other procedural language. The fundamental principle is that you want to replace computations with more efficient methods that produce the same results. And then I have this very, very oversimplistic description where I say, so optimizations that eliminate undefined behaviors are good, and optimizations that introduce vulnerabilities are bad, right? So it's pretty basic. So the C standard has something known as the as-if rule, and this basically says that compilers will, so standard specifies the results as if on this abstract machine that's very detailed, but doesn't specify the methods that implementations must follow. So in the abstract machine, everything's evaluated as specified by the semantics, but actual implementations really can choose any method they want that produces the same results. So this gives compilers the leeway to remove code that's deemed unused or unnecessary when building a program. And one of the peculiarities of this industry is that code that's added with security in mind is the code that's most frequently removed by the compiler. And the reason for that is most security vulnerabilities involve undefined behavior, and while testing for undefined behavior is very easy to invoke undefined behavior. And once you invoke undefined behavior, your code can be optimized out. So there's 3 general strategies compiler writers will follow to generate code. So the first is the hardware behavior, in which the compiler just generates the corresponding assembly code, and you let the hardware do whatever the hardware does. And for a long time, that was really how C worked. So, old programmers are very familiar with that type of implementation strategy. A second is super debug, and here you basically try to trap as many undefined behaviors as you can to assist in testing. But that type of policy really degrades performance, so it's not useful as a runtime protection mechanism. And the third is the total license. So here you'll treat any possible undefined behavior as a can't happen condition, and that permits very aggressive optimizations, and that's sort of what we're talking about. So if you look at a particular compiler, what you tend to find is that compiler writers don't really have sort of strong belief systems. So you'll find a loop, and loops are a good place to look for optimizations because compiler writers, optimizers are really kind of focus in on loops because it's a good place to gain, make performance gains. So you could look at a loop that basically implements a hardware model, and next to it will be a loop that looks almost identical but will implement a total license model. And so compiler writers tend to be very pragmatic and sort of do whatever they want whenever they want to do it without necessarily a real strong underlying philosophy. So the philosophy is you have these compilers and they tend to grow up with different code bases, right? And so the compiler is developed to compile the code that people use that compiler to build, and so these code bases and compilers kind of grow up hand in hand, and that's the pragmatism involved. So a very simple optimization to kind of get warmed up is constant folding. So this is the process of simplifying constant expressions at compile time. Constant expressions can be simple literals like the integer 2, variables that are just not modified, or variables that are explicitly marked as constant. And so here's my example again. I have int min remainder -1. So if you compile that, you're almost definitely going to get the result of 0, which is mathematically what you would expect. So if I look at this with Microsoft Visual Studio, and this is with optimization turned off, what happens is it simply prints the value 0, right? So there's no attempt to perform that calculation at runtime. This is basically a runtime constant expression. So the preprocessor determines what the actual result of that expression is and inserts that instead of performing a runtime calculation. So, unfortunately, if you're doing like a simple test in order to evaluate what, if your processor faults on that expression or not, you might be misled. So you have to take a little bit of care when writing these sort of tests to make sure you're actually testing the behavior you think you're testing. So in this case, I made the input sort of non-deterministic, so the compiler was required to generate the actual division instruction. And of course, the problem here is that remainder on Intel processors implemented as a side effect of the division operation, and the division operation will fault for int min divided by -1 because that value is not representable in the resulting type. I normally tell people to ask questions as we go along, but this is not a question-friendly sort of environment. Okay. So this is the fun one that we wound up reporting that the Plan 9 developers had an issue with. So C11 basically says that if you have an expression where you add or subtract an integer from a pointer, the result has the type of the pointer operand. So that's generally pointer arithmetic. And expressions where you use the array notation basically translate into a pointer arithmetic expression where you add the pointer to the scaled integer size and then dereference it. So it's just a sort of thin veneer for pointer arithmetic. So what C11 says is that you can, I'm going to try to use a pointer here. So it says you can form pointers to each element of the array, including the 1 too far element of the array, and that you can dereference all these elements except the 1 too far. And so this is a little interesting artifact of the C language, and it was because C programmers used to, write loops where they would increment a pointer and then test if it was pointing to the one element past the end of the array. So when C was standardized in 1989, the committee decided to allow the creation of this pointer so they didn't break a ton of existing code. So that's why that works like that. But the formation of this pointer or dereferencing this pointer is undefined behavior in the C language. So a programmer might want to code a bounds check, to avoid buffer overflows. So in this example, we have a pointer which points to the start of an array, max it points to the end of an array, and we have a length specified as a size t. So a size t is an unsigned type that's large enough to represent the largest object that can be allocated on a system. And anytime you store a size or length or something, it really should be as a size t variable, and it should never be as an int. So no matter which model you look at, so then we test to see if the pointer plus the length is greater than the maximum size, and that would indicate we're going to perform a write outside the bounds of the array. So no matter what model you consider, there's a bug in this code, which is that for very large values of length, pointer plus length will overflow, creating undefined behavior. So under the hardware model, programmers would expect the result to wrap around, which would produce a pointer to memory, which is actually lower in memory than pointer. So to fix the bug, an experienced programmer who's internalized this hardware behavior model of undefined behavior might write a check where basically they add this sub-expression, which tests to see whether pointer plus len is less than pointer. That would indicate wraparound on the pointer arithmetic. And so there's a kind of some terms here where we say experienced programmers might have this problem. And the reason we say this is if you're trying to change the C standard, there's several arguments you can make. So the first argument is I work for Intel, and we just added a new feature to the processor, and we'd like C programmers to be able to use that new feature. So sort of evolving hardware is a good way to get the language to evolve as well. The second, maybe the third, let's start with the third, is naive programmers tend to make this mistake a lot. And basically, the C Standards Committee does not care at all about naive programmers. So that argument doesn't go anywhere at all. So the argument in the middle is experienced programmers, such as yourselves, might make this kind of mistake, and then they'll give that some thought. So anyway, compilers that follow the total license model can optimize out the first part of this check that we inserted with security in mind. And this is allowed because pointer plus an unsigned len compares less than pointer. So now the compiler is fully aware that for that to happen, undefined behavior has to occur. And that undefined behavior is the undefined behavior described here in section 656. So the compiler can assume that undefined behavior never happens. Consequently, that test is considered dead code, and it can be removed. So the actual optimization involved is simply algebraic simplification. So optimizations can be performed for comparisons between some pointer p and some value v1 and p and some value v2, where p is the same pointer and v1 and v2 are variables of some integer type. So basically, the total license model permits that to be reduced to a comparison between v1 and v2. But if either of those values are such that the sum with p overflows, the comparison of v1 and v2 doesn't produce the same result as actually computing the values and comparing the sums. So the interesting generalization there is that because of possible overflows, computer arithmetic doesn't always obey the algebraic identities of mathematics. So the good news about the C language is it is mathematically based. It's just not the same mathematics that you learned in elementary school. So if we go back to our example and you look at pointer plus len less than pointer, that's the same as pointer plus len less than pointer plus 0. So now we've got a comparison between p plus v1 and p plus v2. That can be simplified to a comparison between v1 and v2. And of course, len is an unsigned value, so it's impossible for len to be less than 0. So this is dead code and can be eliminated. So if you're aware of this problem, it's actually very easy to fix. If it's known that pointer is less or equal to max, which we know in this example because pointer points to the beginning of the array and max points to the end of the array, you can just basically subtract pointer from each side, and now we'll will have len greater than max minus pointer. So max minus pointers guaranteed not to wrap around because we know that pointer's less than max. So this expression has to be evaluated by the compiler. It cannot be optimized out. Okay, so when we were researching this vulnerability, we posted it to the GCC dev list, and thanks to the magic of the internet, you can still Google all this stuff. And I wound up getting called a lot of really bad names during the course of this investigation. And the one person who was sort of the least, not at all obnoxious, but also helpful was the guy who actually wrote the optimization. This guy called Ian Lance Taylor, who leads the optimization group at Google in Mountain View. But one of the feedbacks I got from the list was, this optimization helps out a lot, right? So an example was, if you look at this expression, buff plus n less than buff plus 100, if you compile this with this particular optimization, this will be optimized to a comparison of n less than 100, eliminating the possibility of wraparound in both expressions. So that's probably not a big deal unless one expression wraps and not the other, in which case you'd get sort of the inverse of the result that you were expecting. But really, that original code example is still incorrect because you don't want to rely on compiler optimizations to make your code correct. So the right way to do this is to try to eliminate the undefined behavior by performing sort of the same optimization by hand and just reducing that to a comparison of n less than 100. And so many C programmers wouldn't write this expression, but what tends to happen is these can result from macro expansions. So it's not apparent in the source code that you're going to generate an expression of this form. So the behavior of this pointer overflow changed as of these releases of the GCC compiler and all subsequent releases. And so this was really something that happened during a maintenance release, right? So you got a new maintenance release of the compiler and suddenly your code stops working. And that's sort of probably the biggest issue with undefined behavior. So when the compiler encounters undefined behavior in your code, it's going to do its best to produce some code that's reasonable, but it doesn't really know what you were expecting to get because the behavior is not defined. But what can happen is, undefined behaviors, the compiler is free to modify what happens on each release. And so as they work on so they tend to focus on them for optimization work, and you could get the next release of the compiler and code that used to work will now start to fail. So this particular optimization is performed by default at O2 and above, include optimizing for space, and not performed at O1 or O0. It can be enabled at O1 with strict overflow option, or disabled at O2 with the no strict overflow. And I'm gonna finish a story I started a minute ago here, but so the guy who wrote this optimization is this guy Ian Lance Taylor, leads the optimization group at Google. And so Google has a small number of applications that they run a lot. So they have these farms of computers. And so Ian determined that this optimization would save them a 0.5% execution speed, and that their code didn't have any defects that would be would sort of suffer as a result of this optimization. And so by implementing this optimization that improved performance by 0.5%, they could get rid of 180 machines off the machine floor and save $240,000 a year or something like this. And so there's a very neat argument to make this optimization for, increased performance and increased costs, but it's hard to make the argument about possible security consequences and the fiscal cost of that. And it's also sort of GCC is a good description of GCC because it's kind of the Wild West of compilers, right? I mean, so anyone could get out there and make a change. Well, not anyone, but a lot of people can make changes that sort of benefit their code base and their organization, but might not be sort of the best solution for everyone. So when we sort of identified this problem, Ian suggested, so everyone on the GCC list, besides calling me names, defended this optimization as allowed by the standard, and they're right. This is allowed under the total license policy. But what Ian suggested was that they add a flag that would diagnose this problem. So if your code used to work but now wasn't going to work, if it was going to be optimized based on this undefined behavior, if you use this option, strict overflow, where n is greater than or equal to 3, it will now be diagnosed. And in a way, that's a reasonable solution. Allow the optimization, but have a diagnostic if there's code that's going to be negatively affected. So going through the GCC flags, strict overflow basically allows the compiler to assume strict signed overflow rules are this total license behavior. So any signed arithmetic overflow is undefined. The compiler assumes that it can't happen, and that permits aggressive optimization. So for example, a compiler always assumes that I plus 10 is greater than I is always true. And that assumption is valid provided I plus 10 doesn't overflow. So when strict overflow is in effect, any sort of attempt to determine whether an operation might overflow has to be very carefully written not to actually involve the overflow. So this is enabled at O2, O3, and OS. So FRAP-V instructs GCC to assume signed arithmetic overflow of addition, subtraction, multiplication will wrap around. It's very similar to no strict overflow, and the flag disables optimizations that assume integer overflow behavior is undefined. And this option's required by the Java front end, which specifies integer overflow as wraparound behavior. So this strict overflow equals n. This is the option that lets you know when these optimizations are being made. So it warns about cases where the compiler optimizes based on the assumption that signed integer overflow does not occur. And it only warns about overflow cases when the compiler implements the optimization. So basically, you need to compile with this flag and with O2. So you need optimization turned on for this flag to diagnose something. So if the optimization isn't being performed, you'll get no warning. So optimizations which assume signed overflow does not occur are safe as long as it doesn't overflow. So a lot of times these warnings can give false positives. And this is sort of a general sort of attribute of C, right? I mean, so you can take a long int and put it in a short, and the compiler says, sure, why not? And the basic premise of C, one of the principles is trust the programmer, right? So the compiler's thinking, well, that looks kind of risky, but I assume the programmer knows that the value they're storing in this long int is within the range of a short int, and so this assignment will succeed without, loss of value. So these can be false positives, but the programmer has to make sure that they are. So at strict overflow equals 1, this warns about cases which are questionable and easily avoidable. So for example, x plus 1 greater than x. With strict overflow enabled, that will be simplified to 1. And this level strict overflow is enabled by the wall flag, but higher levels are not, right? So this is really the most unfortunate thing about this, which is the optimization we looked at that's going to eliminate your buffer overflow check will not be diagnosed with just wall enabled, right, which is what a lot of developers do. So you need to know one of two things. You need to know how to identify the problem and code it correctly, or you need to know to set strict overflow equal to 3. And both of those things are rather improbable unless you sat through this talk and I explained to you that you need to do one of those things. So this is still a fairly common problem with a lot of code bases. So strict overflow equals 2 warns about cases where comparisons are simplified to constants. So for example, absolute value of x greater than or equal to 0, that generally looks like it should be true, but if you take the absolute value of int min in a 2's complement representation, that will overflow to int min, which is less than 0. So this sort of so this code, which could be false, is going to be just optimized to be return true. So strict overflow equals 3 warns about cases where a comparison is simplified. For example, x plus 1 greater than 1 simplified to x greater than 0. And that's the lowest level warning that will detect the buffer overflow check problem that we identified. Strict overflow equals 4 warns about other simplifications. So for example, x times 10 divided by 5 is simplified to x times 2. And in general, I'd be hard pressed to think of situations in which you didn't want this optimization to be performed. And strict overflow 5 also warns about cases where the compiler reduces the magnitude of a constant. So for example, you might have a compiler in which greater than and greater than or equals comparisons cost exactly the same, but maybe an increment operation is a little bit cheaper than an addition operation. And so on those sort of targets, the compiler might change x plus 2 greater than y to x plus 1 greater than or equal to y. So this is only reported at the highest warning level because it could generate a large number of false positives. So one of the things that I've been involved with, so I mentioned I joined the C Standards Committee about a decade ago, and my plan was to change the C language to make it more secure. But of course, what mostly happened was that C language changed me. So one of the things that we did succeed in doing was introducing the Annex L, analyzability annex, into the C11 standard. And so we wanted to call this the security annex, but you're not allowed to do that because if you call anything security, it sort of implies that the C language is insecure. And that's true, but you're not allowed to imply it. So we had to call it the analyzability annex. So we introduced some definitions. So first of all, an out-of-bounds store is just an attempt to modify value outside the bounds of an object or to access a object that's declared volatile. So then we define 2 versions of undefined behavior. So there's bounded undefined behavior, which is undefined behavior that does not perform an out-of-bounds store, but might perform a trap or might produce an indeterminate value. And if you read an indeterminate value in C, that's undefined behavior. So, and critical undefined behavior, which is undefined behavior that's not bounded. And so in the current version of C, there's about 200 plus explicitly defined undefined behaviors. And all of them are, by these definitions, critical undefined behaviors. And so what we did by sort of creating these 2 definitions is that we we restricted the list of critical undefined behaviors to these 8. So these 8 can result in out-of-bounds rights, and the other 292 plus undefined behaviors are now bounded undefined behaviors that cannot result in writing outside the bounds of an object. So this is true, if and only if Annex L is implemented by the compiler, and I don't yet know of any compilers that support Annex L. So, but it's presumably a good idea. Okay, so summary and recommendations. I'm running a little faster than usual because of the lack of questions. So and this is kind of obvious, but you really want to avoid undefined behaviors in your code, even if your code appears to be working. I've had this discussion. I had this discussion with a professor at some university where they had some code that had undefined behavior, and I sent them an email, and I said, this code you're teaching your students has undefined behavior. And he said, oh, no, I tested it, and it works okay. And then I decided that this guy was someone else's problem, because it's just, you can't just do that all day long. So I think a good piece of advice is to find and eliminate dead code yourself instead of letting the compiler do it. When you write code, normally the intent is that code does something, right? So you don't write code that is where the intent is for it not to do anything. So if it's not doing something, that usually indicates there's a logic error. There are sometimes people write dead code on purpose, and a good example is a default clause in a switch, right? So you'll have an enumeration of types, you'll have a case for each enumeration, and then you'll write a default clause. So in well-written code, that default code is a dead code because it's never going to be executed, and the compiler will optimize it out. But it's there in case a maintainer adds another value to the enum, but fails to add the additional case switch. That default clause might then detect that error at runtime. So it's basically a defensive programming strategy and not bad code to have. So the fact that that code gets reported as dead code, that's okay. It's dead code that was intentionally written as opposed to dead code that was unintentionally written. So when you look at all these optimizations, some of them eliminate undefined behavior, some of them might introduce vulnerabilities. So sort of the surprising conclusion I have, because when you get to this part, a lot of security people make the wrong decision, right? Which is they tend to be very dogmatic and say, turn off anything that might ever cause a problem ever. But generally speaking, optimizations do more good than harm, right? So they actually eliminate a lot of undefined behaviors from your code, and they also make your code run faster, which is cool. So with that additional performance, you might be able to afford some more security checks. So, gaining performance is always a positive. So my recommendation is, go ahead and build with these optimizations, but use the strict overflow flag in order to diagnose these optimizations and see whether the compiler is making assumptions that are inconsistent with your assumptions. And what that means is that your assumptions were wrong. So then you need to revisit your code. And my last piece of advice is, tell your compiler vendor to implement Annex L and then use it. So in summary, the C standard is a contract between compiler writers and programmers. The contract is constantly amended, but really only compiler writers show up to the meetings. So it's sort of like getting divorced from your spouse and saying, no, you go ahead and take care of the agreement. I trust you, that you're not going to screw me over. And that doesn't usually work. So, unless more security conscious groups sort of participate in the process, the overall tendency is for the standard to get worse from a security perspective, right? So we like to go to bed thinking things are getting better, but actually they're getting worse. So all these compiler writers, they like to eliminate guarantees from the standards, and the more guarantees they eliminate, the more room they have for further optimization. And so that's sort of the overall trend. The trend is not towards greater security and predictability of execution. Okay, that's all I have. This is how you get in touch with me if you have additional questions. And what do I do now? Do I take questions for a bit? Yep.
I have a question related to sequence standard, and that Microsoft Visual C++ compiler injects the OSV some code that collect and send telemetry. Like, I just want to know what you think about that. Have you heard about this issue?
No, I haven't heard about it. I haven't seen it.
Like you can imagine that your compiler inject the code that collect and send some data outside, just without you knowing that. So the only way is to reverse engineer your own program and get out of it. They say that if you don't want that stuff in your binaries, you have to explicitly set some kind of no telemetry flag.
Yeah. So this gentleman was claiming that Microsoft Visual Studio compiler adds telemetry information to the code it compiles, and if you want to turn that off, you have to find a flag. So
What do you think? Because it's not related to the standard or kind of it's like the problem of someone who create the compilers, they want to collect some information about something.
yeah. So I'm going to give you my sort of strict interpretation of response to that, right? Which is, I would say that would be allowed if there were undefined behavior in your code. But send me an email on that. I'll look into that. It's interesting. Any other questions? Yeah. Yeah.
Has levels, and WAL, of course, as you point out, sets the level for one.
Yeah.
What is the theory behind having levels rather than separate flags for separate types of overflow behaviors? Because then WAL could include all of the overflow behavior warnings if they're one of the levels.
Oh, well, so the levels are, how do you say this? So the question is about using overflow levels versus separate flags. So the levels are, I want to use the word cumulative. I'm not sure that's the right word. So if you set to level 5, you get everything, all 5.
But there's not really an increasing sort of scalar goodness or something. There are actually different types of overflow behaviors.
Yeah.
And this is why the WAL can't catch all those warnings, because there's this scalar. Unless you had WAL say, the scalar has to be the max for all warning levels.
Right. I mean, it could be set to 5. And so, this is not entirely scientific, but sort of, but basically the levels are meant to be, sort of decreasing chance of false positive, right? So at level 1, it's likely that it's a true positive, and as you increase the levels, you're going to produce more false positives. So it's a trick to reduce the number of diagnostics that the programmer sees, because programmers, are prone to ignore warning messages, and so if you give them too many warning messages, they might simply turn it off. So, my kind of recommendation with the levels would be start with level 3 and try to address those warnings. And then you might try setting it to 4, kind of see what happens. And if it looks too intimidating, you could back off to 3 again. But I would at least look at the 3.
But the worry is that, of course, there's this continuum of organicness from compiler writer
Yeah.
to
Yeah, that's true. But and it's, there's a lot of things in life that are unfortunate, right? But I mean, the parallel I'm thinking is I started playing guitar when I was 5, and so I got a $70 guitar, right? Which they're impossible to play, right? But you're not going to give your 5-year-old a Fender, So the amateurs kind of have the worst sort of tools in a way. Okay, any other questions? There was some more, yeah, there. Well, there'll be some additional runtime overhead. I don't know if you mentioned that. Well, that's the greatest concern is the runtime overhead. So so that list of critical undefined behaviors that was very carefully negotiated over several years and a lot of back and forth, and it sort of surprised me how much pain went into that, given that no one's implemented the annex yet. So there are. So I'll give you a quick example. So say you have a Boolean, and you have an array with 2 elements, right? So you'll take the Boolean and use it as an index into the array. So now the problem with that is a Boolean's typically at least a byte, and so there's a lot of values that can be represented besides 0 and 1. So compiler writer might just take that value without checking it and index the array, and if that value were something other than 0 or 1, you'd have an out of bounds write. And so that sort of behavior would be disallowed under Annex L. So now there's some additional runtime checks and so forth you need to do to make sure that Boolean is actually true or false and doesn't have a different value. I don't, because it hasn't been implemented. So we can't run the spec benchmarks and come up with a comparison. Okay, sir. Yeah. Yeah. No, I agree with that. I mean, because a lot of obfuscation techniques, right, insert code that you don't need, and optimizers remove code that you don't need, right? So there's sort of an inverse process to. Yeah. Well, yeah. So if you're depending on, so in C language, right? Unsigned integer wraparound is well-defined behavior, and it's required to wrap around. Signed integer overflow is undefined behavior, and so it can be treated like we discussed. And something I glossed over in the talk a little bit, which is kind of odd, is that the strict overflow flag and a lot of those flags deal with behavior and signed integer overflow. But the actual undefined behavior in the wraparound, the buffer overflow example, was not integer overflow. It was undefined behavior that results from adding a pointer to an integer and it being outside the bounds of an array. But it was sort of thrown into the same category with the integer overflow because most programmers don't sort of separate out those concepts. So it's a little bit confusing. So even Ian Lance Taylor at Google kind of blurred the correctness of this by adding that flag to the integer overflow flag. Okay, any questions down this side? I haven't been looking that way so much. It's because you guys are still hungover, I guess. Let me look back there. Hey, sir? I don't know of any current efforts to implement it. Maybe someone's working on it and they're keeping it below the radar. Any other questions? Guess I should repeat the questions so people can hear. You want to know if anyone was implementing Annex L. Okay, no further questions. Starting to feel like I'm done then. Yeah? Okay, thank you.